Welcome to the central force problem. Today we are going to discuss the equivalent one-dimensional problem and classification of orbits. Previously we have obtained the integrals of equations 318 and 320, which are formally the solution to this motion in a central force field, but they are generally not tractable. However, plenty of information can still be obtained by studying these equations, even if we do not have access to a complete solution giving the laws of motion as a function of time. So, for example, from the conservation of energy, we can obtain the magnitude of the velocity immediately as the expression here. And from the result 316, we can also infer the direction of v from its simple decomposition in radial and angular components. And one can reach the same conclusion for the relation between the angular velocity and the angular momentum together with equation 316. Now, from equation 3.12, we can essentially write Newton's second law as here. So mass times the radial acceleration is given by the sum between the applied force and the quantity here. So L squared divided by the mass times the cube of the radius, and together this can be considered a so-called fictitious force F prime. And to understand the physical significance of f prime, we need to look at the ratio here, which is simply given by this expression by virtue of the value of L, and this is just m over r times the angular component of the velocity squared. So this is just the centrifugal force. As such, using the result 315, we can define a fictitious potential being given by the sum between the real potential and the term here, so half of L squared divided by mr squared. And what follows once again from result 315 is that the total energy can be written as the sum between the radial kinetic energy and this fictitious potential V prime, which contains the real potential and a centrifugal term. And to illustrate the consequences of such an analysis, in the following we are going to consider as an example the specific case of the gravitational force. So to this end, starting with this expression of the force, the fictitious potential immediately obtained is the one sketched here. So this is the fictitious or effective potential, which we can write as v primes or effective v as a function of radius. And these are its two components. So the dashed line here is just an inverse power law for the potential. This is -1 over r. And the dashed line here is just the centrifugal term. And their sum is the continuous line. And along with it, we have also drawn 4 values of the energy corresponding to 4 instances of motion where this value is conserved, and we can just by looking at the figure, we can analyze the qualitative features of the motion, and these features will generally remain true for any kind of central potential that we are studying. So, for example, in the case of the energy E1, the motion is clearly unbounded. That is, the particle comes from infinity. It gets repelled by the centrifugal barrier at some radius, which is generically called the perihelion radius, and then it will return to infinity. In the particular case of the gravitational field, this trajectory is a hyperbola, and it is specifically of interest in scattering theory, particularly in Coulomb scattering, where the force law is the same as in the case of gravity. It varies as 1 over r squared, being either attractive or repulsive, depending on the case. Now, this nature of the motion remains true for the limiting case where the energy is equal to 0. So once again, the particle comes from infinity, is repelled by the centrifugal barrier at perihelion, and returns to infinity. In the particular case of the gravitational field, the trajectory in this case is going to be given by a parabola, as we will show later. Now, in case of negative energy, as is illustrated by the line corresponding to E3, the motion is bounded. So the radius vector oscillates between the points corresponding to two circles, one the minimal radius at perihelion and the maximal radius located at aphelion. And typically this is all that can be said initially by studying the figure, but in the particular case of the gravitational field, the motion taking place between these 2 points is located on an ellipse. And it should be noted that another designation for these points is that of apsidal distances, which we will use in the future. So for any energy that is bound between two turning points in a gravitational field, the orbit will correspond to an ellipse. And in the case of the smallest possible value of the energy, which corresponds to the minimum of the effective potential, the motion here will simply be given by an orbit corresponding to a circle. And this will be true for any kind of potential having a minimum, since the radius is fixed, so the motion is always going to be a circle. Now we can consider another example with a potential given by an inverse cubic law, so minus some constant divided by r cubed, and then the corresponding force is once again attractive, but it's not an inverse square force, but rather an inverse fourth power of the radius force. And we are implicitly assuming that the constant A is positive. And once again, if we sketch the corresponding potential, so the function here, the inverse cubic potential, is drawn by this dashed line, while the centrifugal potential follows from the line here, and their sum is the fictitious potential drawn by the continuous line. And as can be seen, for any value of the energy, there are two possible cases really. So for energy that is lower than the maximum of this fictitious potential, for initial conditions where the initial radius is greater than the value here, the motion is unbounded, so the particle comes from infinity, is repelled by the barrier, and returns to infinity. But for an initial radius that is smaller than the corresponding value here, the orbit is unstable, and the particle will collapse on the center of force. And obviously, initial conditions that would find the particle inside the barrier are not possible classically, as they would correspond to imaginary values of the velocity. Furthermore, circular motion is possible in this field if we are located precisely at the top of the barrier, but it is clear in this case that we speak of of an unstable orbit. So a very small oscillation around this maximum value will result in the particle either being ejected to infinity or collapsing on the center of force. And as a third example, we can look at the radial harmonic oscillator. So the potential is k over 2 multiplying r squared. The corresponding force is minus k times r. And the potential is given by this dashed line. The centrifugal barrier will be given by this line, and their sum, the effective potential, is the continuous line. And we see here that in this case, motion is always bounded. And it is very simple to understand it because in this particular case, it corresponds to with two one-dimension, the composition of two one-dimensional oscillations, one on the x-axis and one on the y-axis. And the resulting orbit is given by what are known as Lissajous figures. And the simplest of them are classified as follows. If these two oscillations are in phase, then the particle oscillates along a straight line. If they are out of phase by 90 degrees, the particle will move on a circle, and for any phase shift in between, the particle will be found on some ellipse between these two extremes. So, in conclusion, we have used the conservation of angular momentum to reduce the motion of the central force system under study to a one-dimensional problem by defining a fictitious potential. We studied the qualitative features of the orbits in various potentials, such as the Kepler potential, the inverse cubic potential, and the harmonic oscillator. For the harmonic oscillator, we have deduced that the orbits are linear, circular, or elliptical, depending on the phase shift between two perpendicular oscillations. In the following, we will discuss the Virial theorem. So, with that being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.